Hello everybody, and today we'll be talking about chapter 2.1 to 2.2 of lecture 3. Let's give a brief overview of this section by first talking about Schrodinger's cat. Essentially, the quantum world, which is the absolutely small world, behaves a lot differently from the world which we can see, which is the macroscopic world. In the macroscopic world, either something emits energetic particles or doesn't, and in the quantum world, which contains electrons, which are immeasurably small, 9.11 times 10 to the negative 31 kilograms, something can either both emit or not emit electrons at the same time. This is related to the cat thought experiment, which is Schrodinger's cat. A cat is placed in a steel chamber with radioactive atoms within. And these atoms either emit particles releasing a flask with poison, causing the cat to die, or they do not release the flask with poison, and the cat lives. Since the chamber is closed, the system is unobserved, and we do not know the result. Therefore, the cat can be said to be both dead and alive, since the result is uncertain. And this cat model is similar to the way electrons behave in the quantum mechanical model of the atom. And so let's talk about the nature of light. Light has a wave-particle duality and is a type of electromagnetic radiation, or EMR. This electromagnetic radiation is made up of a magnetic field, which is a magnetic particle that experiences force, or an electrical field, which is a charged particle which experiences force. An electromagnetic radiation is a wave made up of oscillating, perpendicular, electric, and magnetic fields moving at the speed of light, or 3.00 times 10 to the 8th meters per second in a vacuum. As you can see, here we have a picture of electromagnetic radiation with the electrical field component in red, and this is perpendicular to the magnetic field component, which is in blue. They both head in the same direction, and as you can see, they are perpendicular to one another. It looks a little bit to me like DNA. And now let's talk about what makes up the wave itself. Wavelength is the distance between crests, which is right here, or you can say distance between trophs, which is right here. Amplitude is the vertical height of crest from origin. Remember, it's not the height from troph to amplitude, troph to crest. That would be two amplitudes. However, I don't think we really use amplitude that much in this context. And frequency is the number of cycles or crests that pass through a point in a period of time. So let's say I had a point here and the wave was moving. The number of crests I would see would give us the frequency. A faster wave gives us a higher frequency. However, a wave with shorter wavelength also gives us a higher frequency, as frequency and wavelength are inversely proportional. The larger the wavelength, the farther crest, the fewer crests passing through a point in a given period of time, which means lower frequency. And the opposite is also true: shorter wavelength, closer together the crests, more crests passing through a point, higher frequency. As you can see, different wavelengths produce different colors, and different amplitudes produce different brightnesses. We will talk about this later on, the colors part. For this, we can derive the equation nu equals c over lambda. How I like to remember this: what's nu? C over lambda, where nu, or v, as I like to say it is equal to frequency, which is seconds inverse. C is equal to speed of light, 3.00 times 10 to the 8th meters per second. And lambda, which is a wavelength, is in meters. And also remember, wavelength can also be given to you in nanometers. However, if you want to use this equation, you're going to need to convert everything to the same unit. Since speed of light is in meters, it's easier to convert wavelength into meters as well. Here's an example that incorporates this nu equals c over lambda equation. Calculate the wavelength in nanometers of a red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th seconds inverse. Feel free to pause the video if you want to solve it on your own. We're going to move on now to see the answer and how you actually do it. So essentially what you do, you write down the equation, nu equals c over lambda. Frequency, which is nu, is equal to 4.62 times 10 to the 14th seconds inverse. C, as you know, is the speed of light, 3.00 times 10 to the 8th meters per second. Plug and chug, nu is equal to this, c is equal to this. So essentially what you do, you move lambda over to the left side, divide the right side by the nu actually. So you have lambda is equal to c over nu, which is 3.00 times 10 to the 8th divided by 4.62 times 10 to the 14th. And so what you get from that, you get 6.49 times 35 times 10 to the negative 7th meters. However, they want the answer in nanometers, so convert it to nanometers. There are 10 to the 9th nanometers per meter, which will give you 649 nanometers. Remember, 3 sig figs, because frequency is 3 sig figs. And visible light is a small part of the electromagnetic spectrum. So the part we can see is actually a small part of the entire spectrum. And the spectrum ranges from radio waves, 10 to the 5th meters, to gamma rays, which are 10 to the negative 15th meters in length. And the order of electromagnetic radiation goes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, gamma rays. And this is in order of increasing frequency, decreasing wavelength, or you could say increasing energy as well. And remember this mnemonic, this is the one I like to use. I know there's other ones. Red Martians invade Venus using X-ray guns, where red equals radio, Martians equals micro, invade equals infrared, Venus equals visible, using equals ultraviolet lights, X-rays equals obviously X-rays, guns equals gamma. And here's a picture depicting the electromagnetic spectrum. As you can see, low frequency to high frequency, and then it goes from low energy to high energy, long wavelength to short wavelength. And the colors, remember we were talking about colors before. Longer wavelength colors are reddish, more reddish, and it goes from red to orange to yellow to green to blue to indigo to violet. Violet is the shortest wavelength of light. And since light is a wave, waves can have interference with one another. They can have multiple types of interference, one of which is constructive interference, which is when overlapping waves form a wave with twice the amplitude. As you can see, these amplitudes added up to form something with twice the amplitude of the original waves. And they can also be destructive, which is when the crest overlaps with a trough to form a straight line, which essentially means they cancel out. So as you can see, you add these together. This is negative, this is positive, they're in the same amplitude. It will give you nothing. It's zero. There's nothing here. And these waves can also exhibit diffraction, which is when they bend around an optical slit when they encounter it. And diffraction through two slits causes an interference pattern. As you can see, this is diffraction of the wave. And a particle does not experience the same diffraction, just goes straight through it. We'll talk about the interference pattern next. So for an interference pattern, each slit is essentially a new wave source, which causes the pattern of interference. This interference pattern shows up as a series of bright and dark lines. As you can see here, they have dark, bright, dark, bright, dark, bright. They're alternating. And at the center, constructive interference occurs, which causes the bright lines. However, where the destructive interference occurs, it's caused by, where the dark lines occur, destructive interference also occurs. So essentially bright is constructive, but dark is destructive interference. And here is something that explains why this happens. As you can see, they cancel out, which means there's an absence of light. And as you can see, they add up together, which means that the light intensity is increased. As we've said before, intensity of the light is related to the amplitude. And light also has a particle nature, as it is dual nature, wave-particle duality. And this was exhibited by the photoelectric effect, which said that metals emit electrons when light shines on them. This was previously attributed to the energy of light exceeding the binding energy of the electron, causing the loss of electron from metal, which was in electromagnetic theory. However, this would mean that the rate of electron loss would depend on intensity of light and rather than the wavelength, and therefore low intensity light would cause a lag time. However, an experiment proved this theory wrong, as it showed that high frequency, low intensity light does not have lag time, showing that low intensity light is not the thing that causes the lag time of the electron loss, or rather is directly related to electron loss from metal. And what was found is that there is a threshold frequency, or a frequency below which no electrons are emitted. As you can see in this graph, there is a threshold frequency, and no matter the intensity of the light, high intensity, low intensity, below the threshold frequency, there is no electron emission. So therefore, the intensity of light does not change the threshold frequency, and high frequency light ejects electrons even in low intensity. The only thing that intensity really affects is the rate at which the electrons are ejected. As you can see, higher intensity light has a higher rate than lower intensity light. However, frequency is the thing that determines whether electrons get ejected or not. And Albert Einstein came up with the idea that light energy must come in packets after seeing the photoelectric effect. From this, he came up with the equation E is equal to hV, where E is equal to energy in joules. H is Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. V is frequency, or, as we know before, nu is equal to C over lambda. Therefore, you can plug in C over lambda instead of V, and you get E is equal to HC over lambda. Sorry, whenever I say V, I mean frequency or nu. And light is made out of photons with energy h nu or hc over lambda. Now we have an example that incorporates this idea of energy, which asks a nitrogen gas laser pulse with wavelength 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? And we have another example which talks about the electromagnetic spectrum, asking you to arrange 3 types of electromagnetic radiation, visible, X-rays, micro, in order of increasing wavelength, frequency, or energy per photon. Oh, sorry, I forgot to give you some time to think about it. Please feel free to pause the video, actually, if you want to solve it. So essentially what happens is you want to calculate the energy of the pulse first, which is given to you, 3.93 millijoules equals to 3.83 times 10 to the negative third joules. And then you want to use the wavelength of the pulse to calculate the energy of a single photon. Since you want to divide the energy of the pulse by the energy of a photon to calculate the number of photons located within the pulse. They give you the wavelength, and so therefore you are using the equation E equals hc over lambda. So the wavelength is 337 nanometers, or 3.37 times 10 to the negative 7 meters. The Planck's constant, which is h, is equal to 6.626 times 10 to the negative 34 joules times seconds. Speed of light, which is c, equals to 3.00 times 10 to the 8th meters per second. Energy of the photon, you just plug this all in, hc over lambda. And you get 5.8985 blah 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 times 10 to the negative 19 joules. Remember, this is in 3 sig figs since wavelength is 3 sig figs. And as I said before, you want to divide energy of the pulse by energy of photon to get the number of photons. You get 3.83 times 10 to the negative third joules divided by 5.8985 times 10 to the negative 19th joules. You get 6.4931 times 10 to the 15th photons, or since it's 3 sig figs, 6.49 times 10 to the 15th photons. For 2.3, you're going to want to remember the mnemonic, which is you want to remember that the mnemonic is in terms of increasing energy. Red Martians invade Venus using X-ray guns. Remember, increasing energy, increasing frequency, decreasing wavelength. So, since wavelength is opposite order of increasing energy, it's going to be the opposite of this mnemonic. So you're going to want to order them in the way that puts the things near the end, near the beginning for wavelength. So since X-ray is near the end, visible light is in the middle, microwaves is all the way at the beginning, you're going to want to flip the order, put X-ray at the beginning, visible light in the middle, microwaves at the end, since the wavelengths are inversely proportional to frequency and therefore inversely proportional to energy as well. X-ray has the highest energy, highest frequency, lowest wavelength. Visible light is in the middle. Microwaves has the longest wavelength, lowest frequency, and lowest energy. Frequency is the same exact order as the mnemonic, just put them in as the mnemonic goes. So microwave, Martians, visible light, Venus, X-ray, X-ray. Remember, higher frequency is equal to more energy, so just follow the mnemonic. Same exact thing for energy per photon. Follow the mnemonic / the frequency order. Microwave, visible light, X-ray. Remember, wavelength is the only one that is really opposite to frequency and energy. Energy and frequency are pretty much in the same order. And so light is quantized, which explains the photoelectric effect. And emissions of electrons depend on whether a photon has enough energy to dislodge it. Therefore, the threshold frequency is equal to phi, which is the binding energy of electron to metal. Thus, we can derive the equation E is equal to h nu, E is equal to phi. Low frequency light does not eject electrons, and we can compare this to the ball breaking glass window analogy. So essentially, if you throw a ping pong ball at a glass window, it will not break, and if you throw a baseball at a glass window, it will break. Let's say the glass window, whether the glass window breaks or not, is the binding energy of the electron. The type of ball, ping pong ball, let's say it's low frequency, a baseball is high frequency. As you can see, the ping pong ball, which is below the threshold frequency, does not actually break the glass, which is essentially the action of ejecting an electron. However, the baseball, which is high frequency, exceeds the threshold frequency and in fact breaks the glass, causing an electron to be ejected. So the excess energy of the photon, which is used to eject the electron, is transformed in the form of kinetic energy. So kinetic energy is equal to h nu minus phi. Remember this equation too. Light is both a particle and a wave. So in conclusion, light can behave as both, and this leads to the wave-particle duality of light.